All right, so we've been talking about limits and working with functions and all that other wonderful stuff, which is awesome. But for all intents and purposes, we haven't done actually any real calculus yet. That starts tonight. So the entire purpose of calculus is to start looking at instantaneous things. So in Calc 1, we focus on differentiation. And derivatives allow us to find the instantaneous change of something at a moment. Okay? So in essence, what that's going to allow us to do, and this is why everybody says, well, it's calculus. And we say, it's rocket science, because it honestly is. It allows us to find the pressures and the speed and the acceleration and all that other stuff instantly. Where in algebra, to find slope, you need 2 points. So to find the change, you actually can find the average change between 2 points, but you can't find it at 1 point, because if you do the slope equation and the bottom numbers are the exact same, you would get 0. And we can't divide by 0. However, we've just now spent the last 2 weeks looking at how to do limits. And limits allows us to get to 0. So what we're going to look at tonight is how we actually take limits and allow us to take that slope equation and go to 0 to basically start to find what is the slope at a specific point, in which case then we can make a tangent line and find the derivative at that point. Next week, we'll actually start looking at just literally how to calculate derivatives. So the stuff that I'm going to show you tonight and the stuff that you're going to do in these topics in ALEKS, after this stuff, you won't use it again, because I'm going to give you wonderful, easy formulas to do all this stuff. But it is really important for you to understand where that came from. Calc 2 moves into being able to find area of underneath the curve. And if you take a curve and you're looking to finding areas, you're looking at finding infinitely thin lines. So basically that the width would be 0, which again goes back to limits and allowing us to get to 0. That's why we looked at all that type of limits. So, all right, so let's look at a problem. So you will see quite a few of these problems that are talked at, which is the difference quotient. And as all intents and purposes, the difference quotient is slope. Because if we look at this equation right here, we look at, I always got to remember to grab that. That equation right there, what does f of x represent? What's another way to say f of x? So that's y. And that's a different y. And that's an x. And that's the x when you plug in that y. So if x was 5, you plug it in there, you get the y. That's slope. So this difference quotient is just slope. What we want to find is, okay, let's look at figuring out how we're going to do it to get down to it being 0 on the bottom. So we're going to take and plug in this to this problem. So what is, so we have negative 5 over x squared minus, what would I get if I plugged in 5 to that?
Negative 1/5.
Yep. Over x minus 5. All right, so now let's take that equation there, and we're going to play with it and simplify it. So let's look at the top first. So we've got, if I get a common denominator, I've got negative 25 plus x squared over 5x squared. If I reverse that, I got x squared minus 25 over 5x squared. So far, so good. So now we take and we can factor out that top piece there. So my top is going to be x minus 5, x plus 5 over 5x squared divided by x minus 5. So I can do my keep change flip. So it's times 1 over x minus 5. So that and that will be gone. I've simplified. The algebra is not going away. The algebra is still going to be here. That's not what I want.
So is that the answer?
That is the answer for the first part. So the first part is x plus 5 over 5x squared. What I'm about to write here. So the first part, it just wants you to simplify it all the way down. So then you can plug in 5 and get the answer. Because the original problem, I plugged in 5, I get 5 minus 5, I get 0, and I can't do it. This right here is the derivative. That is the slope when x equals 5. Okay, that is the equation for it. Here, you're going to plug in 5 and get the answer. So if we plug in 5, I get 10 over 125, which is 2 over 25.
So x plus 5 over 5x squared is derivative of x.
Yep. So I'm going to show you right now. There we go. Okay. Sure. So here is my original equation. That's the negative 5 over x squared, correct? So it's this crazy looking equation. So we just found my slope was 2 over 25. Here is my tangent line at 5. It only touches that equation at 5. So it is telling me my slope at that point is 2 over 25. Now, the derivative, the one we just did here, is only will work for 5 because that was the number we plugged in here. Okay. So this is finding me the slope at that point only. We will get to before the end of the night how to actually find this using this type of formula that we can find all of the derivatives. That will give me the derivative of this entire function for any point. So I can plug in any number I want and find that derivative. That's the goal for today, is to get to that. All right, so in essence, we're looking at, for right now, we're looking at finding the derivative at a single point, which is allowing me to create my tangent line for that. Which I don't think. No. Oh. So the next one is actually doing a tangent line, but not actually finding the tangent line. So we'd have to do that part. So this leads this problem. You will know I'm not going to do a ton of each of these problems because you're not going to do a ton of these problems going forward. And actually, I would wait to do your ALEKS work until next Tuesday because some of these problems, when I show you how to find a derivative regularly, will become easier because you can use those rules to do some of this stuff. All right, so we're talking about the connection between the derivative, the slope of the tangent line, and the derivative. So in this topic in ALEKS, they give you the equation of the tangent line. So the equation of the tangent line is y equals 5x minus 2. At some function. They didn't tell you the function. They just told you that's the tangent line when x is 1/4. And they ask you a couple of questions. So if we look at this equation right here, you'll notice that when that tangent line touches the graph, they're equal to each other, correct? Does that make sense? Because that's actually the definition of a tangent line. It only touches at that one single point. So at 5, my original equation is -0 or -1/5 at 5, right? And my slope or my tangent line equation is also -1/5. So they're equal to each other. The reason why is in this question, it wants you to find the equation of f to the 1/4. We don't have f of x. We do have the equation for the tangent line. And they have to be equal at that point. So you're going to plug in x equals 1/4 to a tangent line equation. So 5/4 minus 2 is -3/4. Yeah. Does that concept make sense? Yes, no? Good. Okay. What's derivative telling me? How's the derivative relate to the equation or the function? It's what?
Slope.
It's the slope. Right, so it's the slope. So in my equation for the tangent line, what's the slope? 5. That is the answer to the derivative at 1/4. So that right there is the slope. because that's how we figure out slope. All right. Does that make sense? Okay. A lot of this is literally getting into like trying to get that concept of what is the derivatives. This one. Okay, let's look at this one. So right at that point right there. What can you tell me about the slope at that point?
Steep.
Okay, it's steep.
It's high.
So steep. What else?
Positive. This is going up.
What are you gonna say?
Yeah, it's
Okay. So here's the problem with trying to figure out that. How did you get up 3/1? Okay. So that's not the slope at that point. That's an average. So this one happens to be a straight line, which they're going to be the same, but not every equation is going to be the same like that. So in essence, what you were doing is we were saying, okay, I'm looking at basically like this point and this point, going, yep, it kind of works. And it works on this one. It won't work on all of them. So that's really the difference between looking for slope and looking for a derivative. The derivative is at one single point. So it was awesome to say that. That's one of those things that like to try to get, it's hard to make that connection sometimes. And that's the piece where we're moving from understanding what slope is to understanding what the calculus version of that slope is and that mindset of it. So it's steep. The other thing you said was it's positive. That's actually very important too. Like which directions it go. Okay, because that's going to start helping me. So it's steep and it's positive. All right, let's see. Let's look at -1 now. So we're right here. All right, so at f is -1. What are some things we know about this one? Not you. All right, less deep. It's shallower. What else? It's negative. Okay. So that's the other thing that's really hard sometimes to get is separating the point and the values of the point from the slope. And we're looking at, okay, it's a positive point, but yes, but it's a negative slope. So we're looking at how that equation is changing. And again, we're looking at the limit. So how does it change going into that point? It's negative going in, it's negative going out. We look at it that way. All right, what about f of 1? What about f prime of 1? Not ones that have answered me.
positive.
It's positive. How does it relate to the other ones we've already found? It's a little shallower than the -3, right? Because if you look down here, what's this question asking you to do? We're going to have to put these in order. Okay, so it's less, or it's it's less than the f prime of 3 in terms of shallow or in steepness. All right, let's look at f prime of 3. What about this one? So that goes back to what he said. When you're saying about constant, we're looking at comparing it to something else, right? So what's another way that we can say constant with only looking at a single point? Zero. Think back to your slope equation, because again, we're all talking about slope. When you have a zero slope, what kind of line do you have? Horizontal, right? So in that case, at that point, going into it from both directions, I have a 0. And the last one, f prime of 5. So that's this one right here. What about this one? So it's steeper than f prime of 1, right? Or negative 1. And it is negative. All right. So let's put these in order. What's going to be the least or the small or the lowest value? Huh? YD. Okay. What's less than 0? Negatives. So I have 2 of them that are negative, right? So those are going to be less. So the question is it B or E? Why?
Because it's steeper slope than
So it's going to have a higher negative number, which means it's smaller, right? Right. So E here, I'll just label these so we can just, and then it would be the B, because that's the other one that's negative. Then what would be next? The 0, right? And now we've got the 2 positive ones. Which is going to go next and which is going to go last? C, and then A. What's the slope right there? Why? Good guess. Anybody else have a guess? Before I explain. Nothing there is wrong. But anybody else have a guess?
I say it's gonna have a slope of 0 because it's just reaching a point of turning to.
What have we talked about before this class? What have we been doing? Huh? Limits. And what did I say at the beginning? We're looking at derivatives. We're in essence taking the slope and we're making the bottom go to 0, right? Okay. So if we're looking at getting closer and closer to that point, correct? Is the slope the same on both sides? No. The slope is 0 coming in from one side, right? And the slope is negative coming in from the other side, not 0. So if the limits are not the same, does the limit exist? No. So the derivative doesn't exist at that point. So we will see a situation. So here's the next part of this one. So if we took a graph that looked like that, and I wanted to find the slope right up there. Now, that limit right there, we're going to say that's the peak. That one is 0. That one is 0. Because on this side, my slopes are positive. On this side, my slopes are negative, right? But as it's getting closer and closer to that point, the points are getting closer and closer to 0. Okay, because it's a nice curve to that point. This side, as it's negative, it's getting closer and closer to 0 coming in from that side. So on the one we just looked at a second ago, it was a sharp point. It wasn't gradually getting closer to that thing. It was negative, 0. It was two separate values. So we could say that was like -3 and that was 0. They were two separate values. They weren't getting closer and closer. So when you have a nice curve, you can get to that point. But when it's a little point like that, the derivative doesn't exist. So kind of a trick question, but yeah. I like doing those things every so often. All right. This question, we can only do it at 5, right? Because they gave me that 5. Let's look at this question. So now this question, the difference quotient is A. So that means when I get my answer, I can technically plug in any letter I want or any number I want, and I'll get the answer. Okay. All right. So take a minute and find me that answer using this equation, that function right there. So, okay, what's G of A? What's the derivative of G of A? There's no letters to plug in. It's -6. Okay. So here's the $1,000,000 question. Could you have found that answer without doing any work?
Yes.
Why?
Because you can get it from the original function.
Why?
The slope is -t. For the function, it's linear. So the entire function has the same slope.
So I didn't expect most people to get it. It's okay. The original function was a linear equation, right? 4 minus 16. Simple, in essence, y equals mx plus b equation. Linear equation has the same slope all the way through, right? Never changes. So the slope of that line everywhere has to be -6, which is the slope of the line. Okay. So we can start to look at, I chose this problem for a reason for that, because I wanted you to make that connection between the two. Most of the problems are not going to be linear, that you're not going to easily be able to find that. Okay. So in this situation, that works. That's why you only got a -6 left at the end, because that's looking for the slope, and the slope in this case is 6. Oh, wrong one. All right, let's do one that's not linear. All right, simplify that equation. Think back to the problems that we've done with square roots, and what was the method that we used to simplify them. Secondary screen. Coming around. Remember, multiply it by its conjugate pair. So the top comes out to be 25 T plus H minus 25 T. So the top ends up becoming just H. Because the 25T and minus 25T cancels out. And then the H and the H cancels out. So it simplifies for that. So now, if I did this as the limit of H goes to 0, because that's in essence what we were doing, how does that change? So if we're looking at the limit as H goes to 0 of that,
The denominator would just be two like terms, which we
Right.
add together.
that goes to 0, right? And then I have 5 squared of T plus 5 squared of T, which is 10 squared of T. Yes.
When I did mine, on the numerator, I factored out the 5, so I made it just a square root of T plus.
Oh, you could have done that. And just ignored the 5 all the way through. But you'd have had,
I made a mistake though at the end, so I'm not sure if it's from that or if I just made it.
yeah, that would have, you could have done that. It still would have come out to be the same answer though. Should have at least. So. All right. Let's do this. All right, let's get a little better understanding of what the slope is. So this topic, you actually have to graph things. So what is the slope down here? So what's the slope on that piece right there? And you can't see it, that's fine. Hold on. Like my pointer is not working. Okay, let's do it this way and then we'll go over and draw it. So what's the slope on that from there to there? They're all linear equations on purpose because it's easy for you to figure these out if they're linear. So what's that slope? It goes up 1 over 1, right? So it's 1. Positive or negative? Positive. So from -3, which is an open circle, to 0, my slope is 1. That's that part of the derivative. And you're going, what on earth? That's not what I wanted to do. So from there to there, it is not 2, 1. It's 1. So this is the part that's going to be hard at the beginning, is making that connection between what's the slope at each point and where it's going. Like, oh yeah, the line's going up. Obviously, it's a positive slope. Yes. But is that slope changing? So think back to that linear equation, right? The linear equation, the slope's always the same. So from here to here, the slope is always 1. Yes, the graph's going up, but the slope's not changing. And that's what this graph is. This graph's telling you what the slope is at that point, not what the equation's doing. It's only telling us what the actual change is at that point. So at any point along this line there, my slope's 1. Then from here to here, what's my slope?
3.
3? I didn't count it. Is that right? Yep. So on this part of the line from here to here, actually, I gotta fix that, but it's okay. My slope is 3. And that should have been an open circle there. That should be it. Open circle there. Let's do the next. So from there to there, my slope is 3. Right? Why are they open circles and not closed circles?
Like you were saying, with
Yeah.
the limit, basically, when it reaches that point, it's a start kind of change at that
Correct.
point. It's 0.
Right. You can't find the derivative at that point. It jumps. All right. What about this part over here? From there to there. It's -1. So that's from here to here. So when you're doing this topic and these problems, all your slopes are going to be straight lines. They're all going to be horizontal because they're linear. They're not changing between those 2 points. So when you look at it, there's your 3 lines. And notice they're all hollow dots because they jump. The x's have to match, though, with those changes. So notice that right here, starts at -3 and goes to 0. This one goes from 0 to 4. This one goes from 4 to 6. So those line up. We got a nice graph in this one. All right, what about this one?
First line, so 3.
So we're going up 3, right? So I have an open dot at 3 to there. It's there to there. Not you. What's the next part? Not you. What's from here to here? 0. So open dot on 0. What about from here to here? -1. So from there to there. Oh, that's not what I want. All right. So the three graphs on the left, the graphs on the right, one of each of those is the derivative of the graphs on the left. So let's look at the equations. Let's look at the graphs. And let's pull some information out of it to see what the derivative is doing. Let's start with f of x. We'll start with the first one. What is that derivative doing on the left side of the graph?
It's getting less and less negative.
Okay, so the left side of the graph is negative. Everybody agree with that? This is going down. So my slope is negative. Okay. And it's getting slower and slower as it's getting closer to that 0 point, right? So as it's getting down to here, bad. I can't get rid of my line. Oh, did it not finish? There we go. So from here to here, it's getting closer and closer. It's negative, but it's getting closer to 0. What about this side over here? This side's going positive, right? And it's going from 0. So it's got one change, right? It's changing from negative to positive once. And it's negative on the left side and it's positive on the right side. So which one of these four graphs over here kind of meet that criteria? See? Negative here, positive here, 0 in the middle. And that's where that one changed, it was right there. What kind of graph is f of x? What kind of graph is f of x? Huh? It is a polynomial. What kind of polynomial? Second degree, so we call that a. Starts with a p. Parabola. What kind of graph is d? It's linear, a degree of 1. One of the things you're going to notice when we start looking at the equations and formulas for it next week is that your degrees go down by 1. So a second degree equation will have a linear degree or a derivative. Third degree function will have a quadratic or a parabola as a derivative. All right, let's look at g of x. What do we notice about g of x?
It's always increasing.
It looks like it's always increasing, right? It's like it's definitely increasing over here. There might be a little spot in here that it's actually 0, but it's never going negative, right? It's always staying positive. Okay. So which graph kind of matches that one? C does. Why?
It's always going positive. Graph C never gets.
Right. And that's the key. That actually is the most important part there. Even though C goes down and then back up, every value there, the Y value is positive. Okay. My Y values are always positive in C. Which is what I wanted to see. Okay, because this graph here, my slopes are always positive. So the graph over here, my slopes always had to be positive. Okay. So this one wouldn't work over here. D wouldn't work because I have negative value. All right, so we've eliminated C and D now. So H of X has to be A or B. The question is, which one? All right, let's look at H of X. How's the slope working on H of X? What's the slope over here? It's going down, right? So it's negative. And then it goes, that part's what? That would be positive. And then it goes negative. And then the last part over here is positive. Okay, so at some point between on the left side of the graph, it's going to go from negative to positive, right? So which one of A or B on the left side of the graph goes from negative to positive? A, right here, negative. At that point there, it becomes positive. And that one was a little quick and then slowed back down. That's where that curve's at. At 0, so it's positive up here, it's negative down here. And then it goes back to positive up here. So we had our negative, positive, negative, positive. So this one was A. I did another one of those. Probably a good idea. Let's do this one. All right. Pick out which ones you think are which. All right, f of x. Why?
Because FX is going down at
Okay, so it's linear, so we're gonna have a constant equation out, so we're gonna have a horizontal derivative. And no, I'm not gonna make it easy on you. G of x. Why?
It starts normal, then goes negative, or the slope is negative, then slope is positive, then it's back to normal. D is normal, then value is negative, value is positive.
What do you mean normal? I don't. I have a really good understanding of what you mean by normal, but I want you to explain it.
Really, I just meant like, slope is 0.
That's right. All right. So yeah, this section right here is negative, and then in essence, that's all positive to 0. Right. So there's my negative part, and then all the rest is positive as it gets to 0. So that's got to be B. All right. H of x.
Oh, sorry.
Why? Why C? You said C first.
I'm in graph B.
So now you get to explain to me why C is wrong.
Because the vertex where the function's slope is 0 happens on the negative side of the x-axis.
Good. So where does it change directions? Here. So that means my graph here has to change where the slope is. Okay, so where things change direction is where your zeros are going to be. So that actually means that if you find the derivative of a function and I find the zeros of that, I can find my mins and max points of any function I want, which is another really good use case of what we're going to look at with derivatives. All right, I kind of touched on this a little bit, but there's a couple topics on it, so we'll do these to drill into it a little bit more. All right. Where's our vertical tangent?
X is equal to -4.
So the option on the table is that's where there's a vertical tangent. Everybody agree with that? And you can't just agree because he's gotten a lot of the other questions right.
You gotta say when -2 also work.
Okay. Those options right? I'm not going to do this, but I read a really funny post on the Reddit thread for teachers today. And this teacher said that what they did is they gave their students a test and they told the class they could only turn in one test. And it was either 100 or a 0. If they got all the questions right, they got 100. If they got anything wrong, it was a 0. The class spent the entire period fighting and explaining and going over every single possible answer to get the answer right. Because it was the most learning he's ever seen in a class period. It's kind of like what I was doing with this question. Like, which one's right? You're not going to get a 0 or a 100, but which one?
Well, you would assume because when you're approaching a left, the slope is kind of evening out with 0 and from the right is the same thing.
Okay, so we're not necessarily looking at slope,
Not the slope, but the
the function. Okay.
the graph is
Where do we typically see vertical asymptotes? Or vertical tangent lines? I should say vertical tangent lines. Is like as asymptotes, right? That's where that line goes up and down, right? We don't have that here. But so at that point, you're right. That one's not going to have it because it does go to two different lines. We're not going to have a tangent line there. The only one that does it is at -4. So that one was right. All right. Which has discontinuities. Okay. -2 and 0. All right. Where is the function not differentiable? So which ones of these places are not differentiable? It's every one you've already marked. It's not differentiable at any of those points. Because, so a vertical tangent doesn't exist because x goes to infinity. So, or your y goes to infinity and your x is 0. So it's like that's what your vertical line is going to be. So you can't have a vertical tangent line as a derivative. The corners we've already talked about, where it's drastically changing direction, you can't have a derivative there. The other ones, -2 is the same concept. It's going to two different values. The ones that would be a little more complicated to get would be the -5 and the 0. Because the slope does exist going into those 2 points. And it is equal. Like it would be the same going, like it would be a continuous slope. Those don't exist because those points are not in the domain of the function. And the domain of the function is going to be the same for the derivative. So if it doesn't exist in the domain of the actual function, it can't be in the domain of the derivative. So those 2 points would not be as part of the derivative. So those would also be not differential. Oh, this is an annoyingly long problem to copy and paste. Last one of the day. All right. So, which statement below best corresponds to the meaning of this? So, f of the value, f of x, or f of some value exists. The limit as it goes from the left exists. The limit as it goes to the right exists. But the overall limit does not exist. So which one of those four statements matches that?
Like you got X equals 2. Or, sorry.
Okay. Why?
Because it exists if you're going from the left or right, but it doesn't exist kind of like the same. If those don't equal each other, then it doesn't have doesn't exist, but
Right. So that would be,
and if this continuity, so if it still has
correct. So this one here, the limit as x goes to x of 0 would have to exist for that one. This one, that would also have to exist. X is not in the domain of f. Well, that right there would mean that f of x 0 does not exist, which that does exist. The kink, the limit of both directions does go to the same point. So that would exist in that situation. So the only one that makes sense is the jump discounted. All right, so for which values of x does the statement appear to be true? We've determined that was going to be x equals -1. This one. All right, so the limit as x goes to x naught equals the value of f of x naught. And the limit as x goes to x naught of the difference quotient equals d. So the limit as it goes to the point equals the actual value, the function at that point. And the tangent line exists. It has a slope at that point. So which one of these makes sense for that? Or let's use process of elimination. Is there one that I can eliminate immediately without even thinking?
The first one,
Why?
because it says that it has a tangent line.
Yeah. And that says right there, there's a tangent line. So I can eliminate this one because of that.
Did the same, or
No, the third one just says it's non-vertical, which is fine. Can I eliminate the last one? Yeah, that's the one I thought of right after. I'm like, okay, it has to be continuous. And that's because of that statement, right? That statement means it's continuous. So I can eliminate that one. All right, so it's one of the two in the middle. Can I have a vertical tangent line? Yeah. This also says it's a real number. Infinity wouldn't count as a real number in that situation for a slope. So it does not have a vertical tangent line. So the actual answer is the one you're trying to eliminate. is a non-vertical tangent line. Because you saw the word non in totally speed out. That's okay. Like I told my stats class, all their errors are English errors. Normally in calculus, that's not the case. They're all algebra errors, but sometimes. All right. So which values does this work for? Okay. Why? Good guess. Why? Yeah. Any other ones?
X not equals -2. Or sorry, X not equals 0.
So -2 is your vertical tangent.
Yeah.
-1 is the jump discontinuity. -3 has the removal discontinuity. They don't equal the same thing. 1 has another discontinuity, and 2 is the kink. So only those two work. All right. Same graph. All right. So the limit as x goes to x naught does not equal the f of x naught. And there is no real number d that the difference function quotient works. So this question, I think, should be easy. If the limit of f of x as x goes to x naught does not equal the f of x naught, what does that mean?
It's not continuous.
The function's not continuous, and there's only one option that says that. We can eliminate that one, and that one. So this is the only one that works. All right, so which values of x naught does that seem to appear to be true? Yeah. So that one, that one, that one. Those are the three discontinuities. Wait, one? Yeah, 2, 3. Yeah. All right. Where is this function not differentiable? Is it differentiable at x equals -3? No, because it's discontinuous. Is it differentiable at x equals -2? Why?
So therefore,
Vertical.
I know that it's blue now, but why is that it's not?
Because you got to remember, we're looking for slope, right? So when you have a vertical line, what's your slope? But it actually, if you look at the function of rise over run, it's something over 0, which doesn't exist. Because your rise is infinite and your run is 0. So that's why it doesn't exist. And differentiation is directly related to slope. That's why. What about x equals -1? A negative what? Oh yeah, sorry, I'm looking at the wrong -1. You're right. So no, it's a jump discontinuity. X equals 0. That's the -1 I was looking at. X equals 0, differentiable? Yeah. X equals 1. Yep. It's got a discontinuity. X equals 2. It's got that kink. So the only ones that would be differentiable is that is 0 and 3, which happens to be the answer that we got for that one. Are they equal the same and the tangent line exists? Okay. Any questions? Yes.
Can you go back to slide 8?
Sure. That one?
The slide after.
That one.
Or yeah, that one. I think I got a different answer.
Because you factored out the 5.
Yeah, from the when you multiply the numerator from the conjugate.
Yep.
The 25 also goes to the h, which
I was
goes
gonna ask
into
that too. Why is it 25?
the
Oh, yeah, you would have had the 25 in the numerator. You're right. You are correct. Which would have solved the issue that yours was wrong. Or now yours is right. So there should have been a 25 there.
and then the yeah.
Which means the final answer is 5/2 square root of t. There you go. Now it matches your answer when you factor out the 5. Which is what was rattling in my head when I was looking at this. I'm like, factor out the 5 is not going to be the same thing. But I didn't catch the error. All right. End this recording.